Right. We have now concluded with the discussion of spherically symmetric black holes, and we'll now come to rotating black holes, which is actually the more interesting subject in view of astrophysics, because we are fairly convinced that all black holes that do exist in nature are rotating. And well, if we ignore the cosmological constant and if we ignore charges, then we would have to solve the vacuum field equation, but now not for a spherically symmetric spacetime, but for a spacetime with less symmetry. And the one which will be, the result which will be of relevance for us is a so-called Kerr metric. So we will now talk about Kerr black holes. So that's a rotating analog of Schwarzschild black holes. It's a rotating generalization. So what we want to find is a space-time with the following properties. It should be, well, if it's spherically symmetric, then we can rotate the metric about any axis, and we will always it will always be a symmetry. If the thing is rotating, then there will be a specified axis, and we make this a z-axis. This will be the axis of rotation. So we still have symmetry about this particular axis, but not about other ones. So the metric will be what is called axisymmetric. And if the object rotates with a constant angular velocity, if it doesn't become faster or slower, then it will also be stationary. And what does this mean in terms of mathematics? It means that we can introduce coordinates of the usual spherical, of the type of spherical polar coordinates, which we denote r, t, r, theta, and phi. And then we must have that the metric is independent of phi. That's axisymmetric. Yeah, it's rotationally symmetric about the z-axis. Phi is a coordinate which is the azimuthal angle with respect to the z-axis. So this is 0, and this is 0. So equal 0. So maybe you remember that this is the defining property of what we call the killing vector field. So if this equation holds, then we say that d by d phi is a killing vector field. And if this equation holds, then d by dt is a killing vector field, named after the German mathematician Wilhelm Killing. So in this case, we have only two killing vector fields, much less symmetry than in the Schwarzschild case. And we want to spacetime with, that is, I should write, that is axisymmetric and stationary, and it solves the vacuum field equation r mu nu equals 0. So the analogous problem for finding the Schwarzschild problem was that we here, instead of 1, we wrote the metric should be spherically symmetric. And then we wrote the vacuum field equation, and we could completely solve this problem. Yeah, we could really solve in full generality the field equation for the case of a spherically symmetric metric. It was automatically static. We didn't have to put this in. This was the Birkhoff theorem. And then we found that it is just a one-parameter family of solutions, parameterized by the Schwarzschild radius or by the mass, which is the same thing. This is really a remarkable result. This means that every spherically symmetric body, whatever is going on inside, as long as it is uncharged and as long as we ignore the cosmological constant outside its Schwarzschild, it's determined by the mass alone. So if the density distribution or the pressure distribution inside the star is completely irrelevant for the field outside, and the thing may even pulsate, it may maybe even be time dependent, as long as it's spherically symmetric outside its inner Schwarzschild, it's completely determined by one parameter, by the mass. Now, if you are very optimistic, you might think that something similar might happen here. So that here maybe you have a few more parameters, not just one parameter like the mass. You would certainly have a second parameter which is associated with the spin of the object. You would certainly have a second parameter. But you might hope that, with these two parameters and maybe a few other ones, you can completely solve this problem. But far from that, far from that. So this is a huge class of spacetimes. And we are very far from having a full overview over this whole class. What we know is only very specific subcases of this class of metrics. And the most important one is a Kerr metric. And so we will not solve this in generality. We will discuss only one very particular solution of this problem. So the Kerr spacetime, let me just write this as a result, is one particular solution. So there's no analog of the Birkhoff theorem for rotating objects. Yeah? It's one particular solution, and it can be characterized by two parameters. We will see this in 20 minutes or so. Characterized by two parameters, which are associated with mass and spin. Yeah, angular momentum of the, let me write spin. And you might ask, by what property is this solution actually singled out? And that's not so easy to characterize. And actually, that's the reason why it took so long to find this. So Schwarzschild was 1916. Kerr was 1963. Almost half a century. He has a step from a non-rotating object to a rotating object. It took about 50 years. So you might imagine that it's not an easy problem to solve. So this was found, let me write this here, by Roy Kerr, New Zealander, in 1963. And well, if you look at Kerr's paper, and if you want to find out in which way he actually found this metric, then you will be rather disappointed, because it's very difficult to read it from this paper. Actually, he gives away very little information. So in essence, he just writes down the result and discusses it a little bit, and it's very hard to see how he actually found it. If you dig a little bit deeper into the history, then you see that the way in which this was found, that Kerr, and at the same time also others, looked for solutions which did not only satisfy 1 and 2, but additional properties. And these additional properties had something to do with a special formalism which was developed just a few years before Kerr found this by Newman and Penrose, and it goes under the name Newman-Penrose formalism. So the Kerr, let me just write this down as a statement. Kerr metric is a unique solution, or unique metric, let me write it this way, with 1 and 2, and additional properties. And one is, the third is that it is what is called of Petrov type D. Let me very briefly indicate what is meant by this. So if you have a vacuum solution, then the curvature tensor is completely traceless. Yeah, all trace terms drop out, because the traces of the curvature tensor are associated with Ricci. And if this is 0, then the curvature tensor is traceless. Then it coincides with what is called the conformal curvature tensor. And for the conformal curvature tensor, you can discuss an eigenvalue problem. And that was precisely what is done most conveniently in the so-called Newman-Penrose formalism. And this D here, this stands for degenerate. It stands for the case that two of these eigenvalues coincide, two of these eigenvectors coincide. Two of the eigenvalues was correct, coincide, so that you have a degenerate situation. And this restricts the class very strongly. It's not so easy to interpret this physically. So it's not so easy to see by what conditions this is actually by what physical condition it is actually distinguished, but mathematically it distinguishes a particular subclass. And for this subclass, if one then adds also that it is asymptotically flat, so that far away from the center you have, it approaches Minkowski space, then actually you get uniquely the Kerr metric. So in this way it can be uniquely characterized. So there is a way of derivation of the Kerr metric. What you would have to do is, you would have to learn this Petrov classification, this eigenvalue problem for the conformal curvature tensor, then restrict to this particular type D solutions, add the condition of asymptotic flatness, make this ansatz, and plug it into the field equation, then you get this unique solution. So this would be a rigorous derivation of the Kerr metric. You can find it, for instance, in the book by Chandrasekhar, Mathematical Theory of Black Holes. But if I wanted to do this here on the board, it would probably take 3 weeks or so. So I will not do this, because I would have to introduce all this stuff on the conformal curvature tensor. So what I want to do is something else. I want to sketch more heuristic approach to the Kerr metric. So instead of these conditions 3 and 4, in particular instead of the condition 3, I will impose some other condition, which is intuitively maybe more easily grasped. And I would then just tell you that if you do a clever ansatz, an appropriate ansatz, that then you can also get the Kerr metric in a unique way. So this is nothing like a derivation, but it is more a heuristic ansatz, which is then justified by the solution. If you look in textbooks, actually many of them just write the metric down. They don't give anything like a derivation. And well, that's perfectly legitimate. What you have to do is, if somebody writes the metric down, you can check that it satisfies the field equation, and then you know that it does what it is supposed to do. But I try to give you at least a certain flavor in which way one could approach the Kerr metric without just knowing the result beforehand. And the idea, the ansatz is here. I will follow a heuristic approach. And what we will do is we'll proceed in a similar way as we proceed as I did in my GR course for the Schwarzschild metric. I usually begin, when I derive the Schwarzschild metric, by writing down the Minkowski metric in spherically symmetric coordinates. And then I ask, in which way can I modify the metric coefficient so that the symmetry is preserved? Then I have the most general spherically symmetric metric. I plug this into the field equation and I solve this. If you do this for the Kerr metric, you cannot do it. You have to replace the assumption of spherical symmetry by something else. And well, what is the heuristic approach? If you have now a rotating object, you might think, well, rotating objects, they are usually flattened, right? So if an object is non-rotating, a star non-rotating, then it's a perfectly spherical ball, you would expect usually. But if it is rotating, then it will be flattened. It will become spheroidal. So maybe it's not too far-fetched to replace the spherically symmetric ansatz by the ansatz that I wrote down the Minkowski metric in spheroidal coordinates, which is adapted to a rotating object. And then I will not modify this in the most general way, because then I would actually get the whole class, and I cannot discuss this. I will try to modify it as little as possible. And I will discuss what are the minimal changes of the metric coefficients I have to make in order to get a non-trivial solution. And actually, the minimal change of this metric then will lead to the Kerr metric if I plug it into the field equation. So I consider what is called oblate spheroidal coordinates. So in a way, one has a feeling that they are probably appropriate for considering rotating objects. So what is this? So instead of the Cartesian coordinates x, y, z, which we have in flat space, we introduce something which is not the usual spherical coordinates. This would have just an r here in front of this, but instead we write r squared plus a squared. Sinus phi, sine phi, sine theta, and r cosine theta. So if you depict this, then you get something like, so let me x and y here and z there. So the whole thing is rotationally symmetric about the z-axis. If for a equals 0, the surfaces r equal constants would of course be spheres. With a not equal to 0, a different from 0, The surfaces are equal constants are ellipsoids, oblate ellipsoids. Okay? And the surfaces theta equal constant, they are no longer cones. In the case A equals 0, they would be cones. Now they are hyperboloids. They are like that. So these are the oblate spheroidal coordinates. And let's just write the Minkowski metric in these coordinates. So for the Minkowski metric, I need dx squared, dy squared, and dz squared. So let me calculate the differentials. So dx is 1 over root r squared, a squared, r cosine phi sine theta dr plus root r squared, a squared, cosine phi cosine theta d theta plus root r squared, a squared, and now it's a minus, sine phi sine theta d phi. And similarly for dy, it's r sine phi sine theta over the root, plus root r squared, a squared, now it's sine phi cosine theta d theta, and the derivative of sine phi is plus cos phi sine theta d phi. And the last one is simple. The last one is cosine theta dr minus r sine theta d theta. And now I can write down the Minkowski metric in these coordinates. So the Minkowski metric is, of course, minus c squared dt squared plus dx squared plus dy squared plus dz squared. And, well, the first term is unaffected. Don't do anything with this. And now let's see. Now I have to square these expressions. So let me collect the terms with dr squared. With dr squared, I get cosine squared plus sine squared. This gives 1. So this gives r squared sine squared theta divided by r squared plus a squared. And then here I get a cosine squared theta. So let me write this in a somewhat more complicated way. Let me write it on one denominator, and it's this dr squared. Okay. Then the d theta squared terms. This is r squared plus a squared cosine squared plus sine squared gives 1. So it's cosine squared theta plus r squared sine squared theta d theta squared. And the d phi squared, these are these two terms up there. Again, sine squared plus cosine squared gives 1. R squared plus a squared sine squared theta d phi squared. Okay. So I can abbreviate this a little bit. What about the mixed term? Well, all the mixed terms drop out. Yeah? Every term where, say, a dr and a d theta are multiplied with each other comes twice. Once with a plus sign, once with a minus sign. And, no, wait a minute, here. Once with a plus sign, once with a minus sign. And here I get 3 terms, dr d theta. These terms together cancel against this here. So if you multiply it out, you will find that all mixed terms drop out. So the coordinates are still orthogonal. Yeah, so these are still orthogonal here. I have no mixed terms, no cross terms. So this is c squared dt squared. This is usually abbreviated as rho squared. over r squared plus a squared. Then I have here the same quantity, rho squared, d theta squared plus r squared plus a squared sine squared of theta d phi squared. And rho squared is what? Rho squared is the numerator here. So this is r squared sine squared theta plus r squared cosine squared theta. This is r squared plus a squared cosine squared. So this is rho squared. This abbreviation will accompany us for all our work with the Kerr metric. It's a common abbreviation, so we should acquaint ourselves with this abbreviation. Okay, that's Minkowski space-time. I'm not interested in Minkowski space-time. I want to describe a rotating object with a mass and a spin. By the way, well, A, this parameter which was introduced here, obviously has a dimension of a length, right? Because r squared plus a squared should be a meaningful thing. So A must be a length. And the idea is that we introduce these flattened coordinates when our object rotates. So for a non-rotating object, we want to have A equals 0. So how could we associate a length with a rotating object? So let me just anticipate that this A, well, it must be a length and it should be proportional to the angular momentum. Now the question is, how could you make out of the angular momentum a length? Well, you divide by the mass times the speed of light. Yeah, if you check this, then we will see that the dimensions are correct. This is, r cross p, right? Length multiplied with momentum. And if you divide by a momentum, then you get a length. M times c is a momentum, right? Mass times velocity is a momentum. So this has indeed the dimension of a length. But I'm jumping ahead a little bit, just to give you an idea what the A will, in the end, what the meaning of the A will be in the end. So now we ask ourselves, can I modify this metric in a way that it satisfies two properties? The first property is, if I send A to 0, I want to get the Schwarzschild metric. Yeah, because for A to 0, if the thing is not rotating, then I want to get back my Schwarzschild metric. And the second condition is that it should satisfy the vacuum field equation. Yeah? And I want to do this without perturbing the symmetry. What I've written down is obviously axisymmetric and stationary. Yeah? No metric coefficient depends on t. So d by dt is indeed a Killing vector field. And no metric coefficient depends on phi. So d by d phi is indeed a Killing vector field. So I want to modify the coefficients only by introducing functions of r and theta, but not of t and phi. And I want to do it in a way that the Schwarzschild metric results when I send A back to 0. So want to modify this metric such that G goes to the Schwarzschild metric for A to 0. And well, what is a Schwarzschild metric? Schwarzschild metric can be written in this way. Let me write it, I explain the symbol little m in a second. Let me write it in this way. When we discussed the Schwarzschild metric before, I usually wrote RS for the Schwarzschild radius. From now on, I will use this symbol little m instead of this, and I'll tell you in a minute what the little m is. dr squared divided by 1 minus 2mr over r squared d theta squared plus sine squared theta d phi squared with, yeah, obviously m is half of the Schwarzschild radius. This means it is gm over c squared. Yeah? The Schwarzschild radius was 2 times gm over c squared. So this is a little m. You see the little m is a length. Yeah? And well, if you use units where g and c are equal to 1, that's what theorists like myself usually do, then the little m is just a mass. Yeah? So the little m is just a mass in geometric units, as one says, when g and c are equal to 1. But in order to be consistent with what I've done before, I think it's a good idea to write it in this way. So that's what we want to get. So, and I do this by trial and error. Yeah? So I want to solve the field equation. So I have to check that this ansatz, which I now performed, that it actually satisfies the field equation. And I do not know this beforehand. So I try to do it in a fashion as simple as possible. So here I want to have something, or let me begin with this here. Here I want to have something, the GRR, which goes towards 1 over 1 minus 2m over r. So what is the easiest way of doing this? So what I have written there is rho squared. This was r squared plus a squared cosine squared theta divided by r squared plus a squared. This, of course, does not go towards 1 over 1 minus 2m over r because there's no m in it. But the easiest way how I can achieve this is by adding just 2m times r. This, in fact, goes for a to 0 towards 1 minus 2m over r. Of course, you can do it in many different ways, but that's the simplest way in which you can do it. Let's try this. If it works, then we are happy. If it would not work, then we would have to try a more complicated ansatz. What about the GTT? Well, maybe the most easiest ansatz would be to write it in this way. Yeah? If I send, no, wait a minute. No, this won't work. We want to have something which for, what do we want? Oh yes, it would work. It would work because there's no a in it. There's no a in it. Yeah, so for a to 0, of course, it would give the right limit. But if you try it with this ansatz, you would find that it doesn't work. You cannot solve the field equation with this ansatz. It's too special. But the next more complicated thing is you can do this here. If you now send a to 0, for a to 0, r and rho are the same. And then you have again 1 minus 2m over r in the denominator. And you will find that this works. So, and then the question is, what do we do with the other metric coefficients? So what do we do with the theta squared term, with the d phi squared term, and do we have to introduce additional terms? Well, certainly we would have to introduce a cross term, a term dt d phi. Why? Because we want to describe a rotating object. If you have a rotating object, then the t lines would twist around the object. So there would be terms, cross terms. The t lines would no longer be perpendicular on the surfaces t equal constant. So we would have to introduce, we would expect that we have to introduce a twist term in order to describe a rotating object. And we write one in addition to this expression. And then you would try with this ansatz if you could satisfy the field equation. And you would find that it's still too special. You also have to modify the d phi squared. So the ansatz is now, which you use. I'm sorry?
The second term shouldn't be 1 minus 2m divided.
Oh, sorry, that's not in the denominator. Sorry, nonsense. And we want that there's a c squared at the minus. That's what I meant. Yeah, that's the GTT of Schwarzschild. Sorry. So our ansatz for the metric is now the following. The metric is minus c squared, 1 minus 2mr over rho squared dt squared. Then plus rho squared dr squared over r squared plus a squared minus 2mr plus rho squared d theta squared. Let me just copy this, but leave a little bit of space. D phi squared, and we certainly would need a cross term. Let's write it gamma. It should depend only on r and theta because we don't want to spoil the symmetry. dt d phi. So that would be the thing which we would try first. And then you would find that you cannot satisfy the field equation in a non-trivial way. This means with a different from 0. And then you would add here another term. and then it works. Yeah? So if you feed this ansatz into the field equation, which was motivated by some suggestions which are maybe not too unnatural, but of course far from being compelling. Yeah, it's just an ansatz. So if you do this, then you will find that you can solve the field equation. So you get now a system of differential equations for these two functions, gamma and beta, and this can be solved. So you can, in a non-trivial way, in a way that it works for a different from 0. And I don't do this on the board, but actually that's not too difficult. Inserting into r mu nu equals 0, that's the equation we want to solve, determines yields solution for beta and gamma, and what you find is indeed the Kerr metric. So that this can be done by a computer program for you, of course. Yeah. If you solve the field equations, then you usually do it with the help of a computer. So you do it, I would suggest, only 2 or 3 times in your life by hand, and then from then onwards you calculate the Christoffel symbols and the curvature tensor with a computer program. It's Mathematica or something like that. And what you get here is, I now write down the Kerr metric. So these are these terms here, dr squared plus a squared minus 2mr plus rho squared d theta squared plus, and here we get a dependent correction term. Let me look this up. Oops. Yes, that's 2m r a squared. So you see it goes away for a equal to 0, as it should be. Oops, sine squared divided by rho squared phi squared. And then we get a cross term, which again is proportional to a. So it goes away for a to 0, minus 4m ra sine squared theta divided by rho squared cdt d phi. So that's the Kerr metric. So it has 2 parameters. They are denoted a and m, and this is a standard notation. That's one of the few the few cases where all the literature uses the same symbols. And well, we know what the m means. The interpretation can be done in the same way as for Schwarzschild. Namely, if you are very far away from the... Oh, let me write this first. This is... oh no, let me write the parameters first. Then I write down that it's asymptotically flat. So the interpretation of the parameter m can again be done by comparison with a Newtonian limit. And you see this term, where you look at this term here. If you divide this by r squared, we have 1 plus a squared over r squared minus 2m over r. So the term with the 2m falls off slower than the terms with the a. Yeah, the a falls off with r squared, this only with r. So this is a dominating term. So if you are very far away, then you still have this, this Newtonian potential term, which can be interpreted in the way we have done it for the Schwarzschild spacetime. So the modification by the a comes one order closer to the center. Then the spin makes itself felt. So m has the same interpretation as before. So this is mg over c squared, and capital M is the mass of the body. And the j, where this can also be compared with, found out by an asymptotic analysis, but actually up to a numerical factor, it is just, just clear from the dimension that this must be j over mc. Yeah, it could be a factor, I don't know, 2 or 4 or something like that, but apart from this, it follows just from dimensional analysis. So you see, you have 2 parameters in the game. Both of them are of the dimension of a length. And well, the interpretation of this here is that it gives you the ratio of angular momentum divided by mass. That's what's sometimes called the specific angular momentum. Yeah? So this is big if the angular momentum is big, but it's also big if the mass is comparatively small. Yeah? So it's a ratio of angular momentum divided by mass. So we have a two-parameter family. So the parametric is, okay, let me discuss some properties. Is depending on two parameters, M and A. It is asymptotically flat. Do we see this? Let's see. Oops. If I'm very far away, then I have, if you remember what the rho square was, the rho square is somewhere written down there. A little bit difficult to see, r squared plus a squared cosine squared theta. So you see if you are very far away from the object, then this coefficient approaches 1. And this coefficient also approaches 1 because this goes away. Yeah, you have this here with a square and here with a power 1. So this goes towards 1, this goes towards 1, and here this goes, this also becomes, yeah, well, if you are very far away, then you get just the Minkowski metric in these spheroidal coordinates. Yeah, if you are very far away, you reproduce the expression which we have written here. Yeah, far away from the center, this goes away because you have r over r squared. This goes away, r over rho squared, and then you end up with precisely this expression. And here even just with 1 in front of the terms. No, the rho squared is of course there. The rho squared divided by this here without these terms. So that's the Minkowski metric. Yeah, that's what you get if you are far away from the center. And this means the metric is asymptotically flat. Oops. What else can we say? Of course, it's axisymmetric and stationary. So the terminology is like that. Stationary just means that d by dt is a Killing vector field, so that the metric coefficients do not depend on t. If in addition there's no cross term, so if in addition the vector field d by dt is perpendicular to the surfaces t equal constant, then we say the metric is static. So static means stationary and non-rotating, without twist. This is not true here, so it's not static, it is stationary. The Schwarzschild metric was static, but the Kerr metric is only stationary. Okay, what else can we observe? Yeah, we see already that there's what happens with the range of the coordinates. There's something quite interesting. So in front of the d theta squared, we had in the Schwarzschild case, we had just an r squared. So if we send r to 0, then this coefficient in front of the d theta squared and also in front of the d phi squared becomes 0. This means the sphere, r equal constant, shrinks to a point for r to 0 in the Schwarzschild case. And that was our singularity in the center of the Schwarzschild spacetime. So we couldn't extend the spacetime through r equals 0. And now look what happens here if r is going to 0. If r is going to 0, this expression does not go to 0 because I have the term a squared cosine squared theta. So it goes only to 0 if r goes to 0 and a cosine theta goes to 0. Yeah? So what is this? R equals 0 and cosine theta equals 0, that's a ring. That's a ring in the equatorial plane. So we have this singularity, and actually it turns out to be a true curvature singularity as in the Schwarzschild case, not at r equals 0, not everywhere at r equals 0, at r equals 0 and cosine theta equals 0. Yeah? So where both conditions are satisfied, at points where both conditions are satisfied simultaneously. And that's a ring singularity. So r equals 0. R equals 0 is a sphere with a finite area. And only in the equatorial plane, where also cosine theta is equal to 0, there we have the ring singularity. Yeah? R equals 0 is a sphere which has a finite area. You can read it from these angular terms. And this means you can extend the metric through this sphere r equals 0 into the range of negative r. Yeah? This was not possible in the Schwarzschild case because we would have to cross a singularity at r equals 0. In the Kerr case, we can go into the area r smaller than 0 without crossing the singularity. We have just to be careful that we don't hit the ring singularity. There we can go through one of these hemispheres here without encountering a singularity. So the horizons I don't get. The horizons I will discuss next time. So these are the things which you can read immediately without doing much calculations. And then we will discuss next time the horizons. So we have to see where this expression here becomes 0. This will give us the horizons of the Kerr metric. And we will see that there might be two horizons. There are also cases depending on A and M where I have no horizon whatsoever. So this will then distinguish the Kerr black hole from the Kerr naked singularity. Okay, so this was a trial to give you an idea in which you can approach the Kerr metric. In essence, what I've done is not much different from just writing it down. So you have to guess what is the right ansatz. I try to give some kind of motivation, but then in the end you have to check if it works. And if it would not work, then you would have to try something else. So in fact, this works. So this is this famous rotating vacuum solution, and we will discuss it in some detail in the next, I would think, at least 2 weeks. And with that I stop. And we have now our tutorial among ourselves, and I say goodbye to everybody who is watching us. Have a nice weekend.